All right, hello everyone. Um, I'd say welcome back. It probably doesn't mean much to you because you're just going these day by day, but it's been a few weeks since I've done one of these. So for me, it's welcome back. Anyway, we're at the beginning of chapter 8. Really quick lesson today, actually, the first one, 8.1. Chapter 8, for lack of a better term, are applications of integrals. So we spent all of chapter 7 learning how to take different antiderivatives in integrals. And so now we're going to do some applications, just kind of like we did with derivatives, kind of like related rates, optimization, differentials. There are things we can do with integrals. So a little bit different than with derivatives, though. So we're going to start with a review one. So we've kind of done this before, but we're going to kind of now throw some integration into it to kind of help you see the connections. So you might remember way back when we did what we call the position function S, position function. The derivative of the position function was velocity. And then the second derivative of the position function, or the derivative of the velocity, is acceleration. So old stuff from derivatives. I wrote a little note over here, position function plus backwards is integration. Just want to show you how we get that projectile motion formula real quickly that you may or may not have memorized, but it actually comes from integration. We just give you the formula. We don't really say a lot about it when we did it. But if you start with acceleration, so we're going to kind of work a little bit backwards. If you start with acceleration, we'll go in feet. We could do meters also, for sure. So the negative 32 feet per second squared. If we integrate acceleration, we get velocity. So we integrate this with respect to time. So we get negative 32 plus c. And if we say if time equals 0, we get what we call initial velocity. So we're going to say the initial velocity equals negative 32 times 0 plus c, which means c becomes the initial velocity. So we get a formula for velocity of negative 32t plus initial velocity. We integrate again, we get position, right? So we're going to integrate again. We get negative 32t squared over 2 plus initial velocity times time plus some constant c. But then again, at times 0, we have our what we call our initial position, or our initial height is what we use for projectile motion, right? So we'll call it h sub 0. So we go h sub 0 equals 0 plus c. Oops, c. So c is h sub 0. So here we go with our position function, negative 16t squared plus initial velocity times time plus initial height. This is the formula we were using back in chapter 2. But there is where it comes from integration. So just today, real quick, a couple of things about integration and velocity. So if you integrate the velocity, we know this, we get the displacement, right? So if you integrate velocity, you get, generally speaking, you get the position, right? But if we integrate velocity from time equals some time a to some other time a, okay, we get how far this thing moved. Remember that velocity or integration is area under a curve. So you can think about this also if we have some graph, right? And this is the velocity graph. If you were to integrate from A to B and you get that area, that is the displacement, how far it moved, right? If it's all positive, we call it total distance traveled, but there could be some positive and some negative. So remember, velocity has a sign attached to it, so it could be positive or it could be negative, which means you could wind up like right back where you started, or in a negative position or a positive position. So I'm going to throw in a little thing here. Sorry, I skipped this. This would be if I integrate this, I get S. Remember, I get the position from A to B. So I get S of B minus S of A. It's where are we at time B minus where are we at time A. We call that the displacement. So if someone says, find the displacement, and they give you the velocity, all you have to do is take the integral from A to B. It's the same thing. Remember, the idea is adding up that area, right? So think about this as being the total. The red is the distance traveled, right? If it's positive, if it's negative, we could, again, add. We could move one direction and move back. If we want to know how far we went, this is another common thing. Like, I could walk across the room and right back to where I started. My displacement would be 0, but I clearly walked. I moved, right? So if we want to find out how far something travels, we then need to integrate the absolute value of velocity, right? So we need to count if I move towards that wall, as a positive direction and back towards this. So if I go 10 feet that way and 10 feet that way, I've walked 20 feet, but my displacement's 0. So I have to know when the velocity is positive, when it's negative. So here's a pretty common problem. Let me erase this. So you got that now. We'll kind of walk through an example problem, then I'll be done. So I have a velocity, 6 sine 3t, a little trig function that's fluctuating back and forth. So these are the typical questions you might get. The two most typical questions are find displacement, find total distance traveled. I threw in when is the particle moving left, right, stop, because you need this to answer that, right? Displacement is the easier thing to do, because displacement, all I got to do is integrate from 0 to 2 pi. So this is displacement right now. This is the easier part. I just integrate the velocity, right? It's all I got to do to get displacement. It's the easiest one to do. So if I integrate this, looks like I'm going to get a negative 2. Let me see, make sure I get that right. I'll leave that 6 there just so you can see it. It's cosine 3t divided by 3, right? So negative 2 cosine 3t. From 0 to 2 pi. I'm going to factor out the negative 2. We get cosine of 6 pi minus cosine of 0. 1 minus 1, which is 0. So our displacement is 0. If you think about this as a graph, it's just a sine curve, right? Just with a little squished because of that 3. So it should make sense. From 0 to 2 pi, we got negative area, positive area, negative area, right? So the displacement is 0 because it's the same positive, negative. If I want to find the total distance traveled, I need to know the positive area versus the negative area. That's why I asked that question, when is the particle moving left, right, or stopped, right? So if you graph this thing, if we wanted to go 6 sine 3t, that's my velocity function. We'll just set that equal to 0 because I'm going to try to find these zeros here. Notice I'm also on an interval from 0 to 2 pi. So we get sine 3t equals 0. So that means 3t equals, sine is 0 at the multiples of pi, right? 0, pi, so 0, pi, 2 pi, 3 pi, so on. But then I have to divide by 3. So I get 0, pi over 3, 2 pi over 3, 3 pi over 3, which is pi. We're going to keep going. We don't really need all these. I'll show you why. So we got 1, 2, 3, 4, 5, 6 of these regions. But notice the symmetry is all the same, right? So if I wanted to find the total distance traveled, I really only have to integrate this first one, which is from 0 to pi over 3. What you would normally do is just count the positive ones. Normally, this is kind of like the problem, if you remember, it was a long time ago for you now. For me, it was just like last week, the one where we asked total area between the curve and the x-axis. You count the positive area as positive. The negative area you just count as positive also. So when you integrate it, you turn it from negative to positive. So normally that's what you would have to do. So normally I would have to go, then I'd go from pi over 3 to 2 pi over 3. But this would be negative area. So I would subtract that. And then I would go from 2 pi over 3 to 3 pi over 3. That's positive area. Then I would go from pi to 4 pi over 3. That's going to be negative area, so I would subtract. That's normally what you would have to do. But because of the symmetry in this problem, I can just go from 0 to pi over 3 of 6 sine 3t. And I'm just going to multiply it by 6 because there's 6 of those regions. We've already done the integral. There it is right there. So it's negative 2 cosine 3t. But then I got the 6 still. So we're going to call it negative 12. And we're going from 0 to pi over 3. I'm going to factor out that negative 12. Cosine of 3 times pi over 3 is cosine of pi minus cosine of 0. So negative 12. Cosine of pi is not 0, but sorry, negative 1 minus 1. So that's a negative 2. So it looks like 24. Notice it's positive. The math worked it all out for us. Yeah. So displacement and total distance traveled are really the two things here. The displacement is the easier question. You just integrate velocity, you'll get the displacement. But if you have to figure out how far it traveled, you got to figure out when the thing's positive, when it's negative, and then treat the negative area as positive area. That's it.